Welcome back to the deep dive. Sometimes the most powerful connections between abstract ideas and the real world are hiding, well, kind of in plain sight.
Or maybe right there in your college calculus notes, yeah.
Exactly. It's
Yeah.
often in the places you'd least expect.
Definitely. Where these fundamental math tools show their incredible utility. What's really fascinating here, I think, is seeing concepts like uh, differentiation and integration applied to something that seems so straightforward.
Like mixing ingredients.
Right. Mixing stuff.
So today we're diving into some source material that unpacks exactly that connection. How optimizing mixing speed in, say, food processing plants actually relies on the very calculus you might be studying right now.
Yeah, this deep dive is particularly relevant if you happen to be a college student, wrestling with those very concepts.
Hmm.
The source material gives us a really concrete look at how these mathematical tools are not just textbook exercises. They're, well, keys to solving practical industrial problems.
Okay, so our mission today is to truly understand how these abstract mathematical ideas connect to the, tangible world of food production.
And importantly, how that connection ultimately links to something really significant, like global food security.
Right. Let's jump in. So the source material gets quite specific about the application, doesn't it?
It does. It highlights that optimizing mixing isn't just like stirring until things look okay.
Hmm.
It's about achieving specific, measurable outcomes. Thinking consistent texture,
Mhm.
uniform ingredient distribution, or even minimizing energy consumption, stuff like that.
And this is where calculus comes into play, according to the source. They talk about modeling these outcomes as functions.
Exactly. So you might model the quality of a mixture, say its homogeneity or maybe its viscosity as a function of the mixing speed and the time you spend mixing
Okay, mixed it
and
in.
differentiation. Well, that lets engineers analyze the rate of change of that quality function.
So how fast the quality is improving or maybe declining.
Precisely.
Hmm.
By finding the derivative and setting it to zero, they can locate those critical points, potential maximums or minimums on the curve.
Ah, like finding the peak of the hill.
You got it. That's how they pinpoint the optimal mixing speed to hit the quality target, or maybe the most efficient speed. It's like finding that sweet spot on the graph.
Okay, so differentiation finds the ideal rate. What about integration? How does that play a role based on the source?
Well, the source suggests integration comes in when you're thinking about the total impact or like the scale of things.
Hmm. Total impact.
Like,
Yeah.
for instance, if you know the rate of energy consumption during mixing as a function of speed or time, integrating that function over the whole mixing period gives you the total energy used for that batch.
Ah, okay. So not just the best speed, but the total cost, energy-wise.
Right. And optimizing that total energy through integration helps cut costs and improve the overall process efficiency, especially important when you're scaling up production, big
Mhm.
factories.
So it's not just finding the best speed for one moment, but potentially calculating total resources used over time, or maybe total output across a huge volume.
Mm.
That detail from the source really highlights how broad the calculus application is here.
It really does. It shows these aren't just like isolated calculations. They're part of a bigger engineering effort to make the whole process as effective and efficient as it can be.
And this efficiency, the source points out, has a direct line to food security. How exactly does that connection work?
Yeah, if you connect this to the bigger picture,
Hmm.
optimizing every step in food processing, including something like mixing, means less waste of raw materials.
Right, less waste.
And more consistent product quality, which means, fewer rejected batches, less spoilage, plus lower operational costs because you're using less energy.
Which ultimately means you can produce more food that people can actually use and maybe more affordably too.
Exactly.
Mm.
On a large scale, these kinds of efficiencies really contribute to making food production more sustainable. And the food supply chain becomes more robust, more accessible.
Mm.
So that calculus problem solved, in a lab or on a computer, it directly impacts the economic viability and the sheer output of food production.
It really makes those differentiation and integration problems you might be working through feel a lot more significant, doesn't it?
Absolutely.
The source material makes it pretty clear these aren't just abstract exercises you learn in class. They are foundational tools for optimizing processes that, well, literally feed the world.
It's a really powerful example, I think, of how mastering fundamental mathematical concepts gives you the language, the tools you need to tackle complex real-world engineering challenges.
So, to wrap up this deep dive, then, we've seen how the source material reveals that differentiation and integration are pretty critical for optimizing processes like mixing speed and food production.
Yeah, by modeling outcomes and finding those optimal points or calculating total impacts.
And crucially, how these seemingly technical optimizations contribute to that much larger, vital goal of enhancing food security around the globe.
It's definitely a reminder that the concepts you run into in college math, well, they have tangible applications that ripple out into the world in some pretty profound ways.
So maybe next time you're grappling with a derivative, or perhaps just enjoying a snack,
Hmm.
think about this. How many other seemingly abstract mathematical ideas might be quietly optimizing the everyday products and systems we rely on?
Hmm. That's a good question.
And what does that hidden optimization really mean for critical global issues like food security? Sure, but also energy use or maybe even public health. Something to think about.